In this video, we're going to configure the pulse NMR apparatus to make a T2 measurement. The way we're going to do this now is when we study the physical mechanism behind T2, what we understand from that is we need to hit the mineral oil sample with a pi/2 pulse or a 90-degree pulse, then a subsequent 180-degree pulse or pi pulse at some delta t later. So we're going to hit the sample with a series of 2 pulses. Again, the first one will be a 90-degree pulse, the next one will be a 180-degree pulse. And by 90 and 180, I'm referring to the total angle that this net spin magnetization will be rotated through upon application of the pulse. So on the oscilloscope at the moment here, I have an A pulse right here, I have the B pulses off, and this is just an A pulse right here. And that's what you see on the green trace. And on the yellow trace, I have the output of the detector from the pulsed NMR apparatus. So what I'm going to do is I'm going to turn the knob of the A width here, which is going to vary the width of this A pulse. And as you know from pulsed NMR, the width of the A pulse dictates how long the RF will be applied to the sample. And the RF has been optimized at about 15.41 megahertz. So here I go, I'm going to start turning up the A pulse width. And what I start to see when I do that is the signal suddenly gets very large. Let me zoom out a little bit on the oscilloscope, see it better. It gets very large, and I would just like to optimize this amplitude. So I'm just wiggling this knob back and forth to make the amplitude as large as possible. That's about as large as I'm going to get. So the application of an A pulse of about this width here gives me a signal of maximum amplitude like this. And I know this will be a 90-degree pulse because I'm rotating the spin from its equilibrium position oriented along the static magnetic field axis, which we'll call Z, up along the XY plane, which is where the detector exists, and so I'm getting a nice maximum signal. So whenever I get those spins oriented parallel to the detector, which is in the XY plane, I get a maximum signal. So I know the A pulse must be at 90 degrees. So now what I'll do is I'll turn the A pulse off and turn the B pulse on, and then I'll tell the device to synchronize or trigger the oscilloscope on just the B pulse also. So this looks very much like what I just showed you, but this is the B pulse now, not the A pulse anymore. But the same thing is happening because the A pulse is off, the B pulse is sort of like taking the role of what the A pulse did. So once again, I'm going to try to change the B width, this pulse width should go in and out to maximize the signal return on the NMR apparatus. Okay? So as I can see, I do that, and if I look down at the A and B knobs, the painted line indicator is at about the same position. So both pulses are currently delivering a 90-degree rotation to the net magnetization of the sample. But remember, for T2, which is what we're measuring this signal, we want the A pulse to be 90 degrees, we want the B pulse to be 180 degrees. So what I'll do is on the B pulse, relative to this timing, I'm just going to keep increasing it until this signal gets minimal, not maximum. And that's my indicator that B is at 180 degrees because I'm rotating it through the plane of the detector all the way, inverting it to the negative Z-axis. So it's exactly opposite to the equilibrium of where the spins would be in the static magnetic field. And because they're not aligned at all with the axis of the detector, I get a minimal signal. So in this configuration, and again, you can look at the paint on the knobs, the little black line there, you can see that the B does look to be about twice A. So I'm pretty confident now that the A is delivering a 90-degree pulse, B is delivering a 180-degree pulse. So I can zoom back out on the oscilloscope, we can sort of see the whole thing happening here. Let me go back to synchronize on the A pulse like this. And if I do this, let me try to find it now. Oh, let me turn the A pulse back on. There we go. So now A and B are both on. Okay. So here's the A pulse doing its thing. And if I sort of zoom out a bit more, let me just see if I can find the B pulse now. Yep, there it is. Okay. Here's the A pulse right here, and here's the B pulse right here, and that's the 10 milliseconds between them. I have 10 milliseconds set here, 2 milliseconds per division, 1, 2, 3, 4, 5, yep, about 10 milliseconds between them. So it doesn't look like very much is happening. Again, there's the 90-degree A pulse, there's the 180 B pulse right there. But if I keep looking, then curiously, I find a signal way over here. And this is always a very interesting part of pulse NMR because remember, this is where the A pulse is actually on, this is where the B pulse is actually on. And what I mean on, when these pulses are on, it means RF is actually getting applied to the sample at 15.41 megahertz. But when the pulses are off, there is no RF. So interestingly, this B pulse is when the last RF ever got applied to the sample in this configuration. And so for all this time right in here, there is no RF applied to the sample, but curiously, a signal pops up. So what the signal is here is an indicator of how long it's taking the individual spins in the mineral oil sample to rephase and just give the maximum possible signal they can on the detector. This is called a spin echo. It's when all the spins suddenly rephase and are able to give a large signal on the detector. So our data in this particular experiment then will consist of tracking the amplitude of this signal as a function of delay time between the A and B pulse. So we'll hit it with an A pulse, we'll delay, we'll hit it with a B pulse, and then we'll just see how large the amplitude is of the return signal as a function of delay time. So we'll set that up in the next video. So again, this is our first look at T2 for pulsed NMR, and in the next video we'll actually get some data coming in.